Hello, my amazing Algebra 1 students. This is your first lesson in Algebra 1, and I am Mrs. Carla, and I have been teaching algebra for a very, very long time. I've been teaching high school algebra for 11 years. Okay, I've been teaching at the college level for like 26 years. And I've even taught at the elementary kindergarten level for 4 years. So I've been teaching for quite a while, and I'm going to teach you Algebra 1. So our very first lesson is on classifying real numbers. And what I'm going to do is I'm going to have the work up on a board, and I will come back and talk to you, and then I'll show you the work on the board so that we can kind of go back and forth. So I'll be right back. So here's our little board, and classifying real numbers is our topic. Now notice the things that we're going to be talking about today. Algebra is a study of mathematics that has its own little language, and we are going to have to learn the words. Now, of course, if you can tell, that's my coffee pot over there, and those are my dishes over there. So I'm right in the middle of my kitchen showing you my board. But I've prepared this lesson for you. So hopefully you will ignore the delivery in the middle of my kitchen and enjoy learning the concepts. So these are some words we're going to learn about: set, finite, infinite, natural, whole, integers, rational, irrational, and real. Okay, and we're going to draw some pictures to talk about these. Now, I'm going to move over here close to the board, and when you first start learning to count, you start to learn 1, 2, 3, 4, ... You start, your mom puts spoons on the table, and you start learning how to count items. Okay, so these are called the natural numbers or the counting numbers. And they are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the first thing you learn, isn't it? How to count to 10. Okay, they're also going to go on and on and on up to infinity. Now, infinity, we can never, ever get there. This is the symbol for infinity. That just means it's as high as you can go and then more. Okay, so we can never get to infinity. But it starts at 1. So then you get a little bit older and you learn the concept of 0. 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 0 is how many cookies you have left when you give them all away. Or as we used to say, how many elephants you have in your pocket. And I don't know about you, but I don't have any elephants in my pocket. Do you have elephants in your pocket? We call these numbers that start with 0 and then go 1, 2, 3, 4 the whole numbers. So the whole numbers include 0 and all of the natural numbers. Then you get a little bit older and you realize, uh-oh, there's this thing called debt. -1, -2, -3, -4, ... Oh my. We can go into debt. Okay? So we have the numbers that are the whole numbers, and their opposites are called the integers. So the integers are the whole numbers and their opposites. And when we think of the real number line, we think of 0, 1, 2, 3, 4, and it continues, ... And we think of -1, -2, -3, -4, And that continues on and on forever and ever. Amen. And we have a real number line. But the real number line does not just include the integers. It includes all of these numbers that are in between the integers. Okay, so the real number line includes all of those numbers in between the integers forever in both directions. Those are the real numbers. Okay, so we're going to work on categorizing these numbers. Now let's look at how many of the little groups we have already talked about and the ones that we need to continue talking about. Okay, here's our board again. We have talked about natural numbers. Natural numbers are our counting numbers, 1, 2, 3, 4, 5. Okay, we've talked about our whole numbers, which is our 0, 1, 2, 3, 4. And we have talked about our integers, which we have a picture of right here. -4, -3, -2, -1, 0, 1, 2, 3, 4, and they continue in both directions. Okay, and then we have already talked about our real numbers. Okay, our real numbers are every number that fits on the real number line. Now, let's look at a couple of things that we haven't talked about. We haven't talked about rational numbers or irrational numbers. Now, when I'm talking about rational or irrational, I'm not talking about whether you make sense or whether you fly off the handle when things don't go your way. That's a different kind of rational or irrational. What we're talking about is rational numbers can be written as a ratio. And remember that a ratio is another name for a fraction. And irrational numbers cannot. They cannot be written as a fraction. Well, let's look at our list of numbers over here. Okay, can natural numbers be written as fractions? Well, remember natural numbers are 1, 2, 3, 4. And any one of those numbers can be divided by 1 and expressed as a fraction. So, natural numbers are going to be rational. All right? What about whole numbers? Whole numbers are just the natural numbers or the counting numbers with 0. Okay, well, 0, you can put a 1 under 0 also. 0 divided by 1 is still 0. Therefore, all of the whole numbers are also rational. Okay, what about the integers? Well, -4 over 1, -3 over 1, 3 over 1, 4 over 1, those are integers, and they can all be written, they can all be written over 1, therefore they are rational. So we have natural whole numbers, integers are all rational. Now, right here, our real numbers cannot all be written as fractions. So we're going to divide our real numbers into rational and irrational and decide what kind of numbers fit in each one. Well, it's obvious that all of our fractions will be rational. Fractions will be rational. What about decimals? What kind of decimals are rational? If you remember, decimals can be turned into fractions if they terminate or repeat. So, decimals that terminate or repeat are rational. What does terminate mean? It means it stops. It ends. At some point, it stops. Okay? So, do you remember how that's done? Well, let's see. This is just a quick review. 32.56. Remember, this is the tenths place, and this is the hundredths place. So I can say that is 32 and 56 1/100ths. But remember how to turn a mixed number back into an improper fraction? 32 times 100 is 3200, and then I add the 56 in there, and I get 3256 divided by 100. So this is a fraction, therefore 32.56 is rational. So we're going to put down here on our board decimals that terminate. I like that word. Don't you like that word? Terminate, which means they stop or repeat. All right, so here's our list of rational numbers. Naturals, wholes, integers, fractions, all the decimals that terminate or repeat. And then we have our square roots and our cube roots and our fourth roots and our fifth roots. Any kind of root that comes out evenly. In other words, square root of 25 is exactly 5. Since 5 belongs in the integers, then it is a rational number. Cubic root of 8 is exactly 2. So since it becomes an integer or a whole number, it is rational. On the other hand, numbers that do not turn into fractions are irrational, like the square root of 24. We cannot turn square root of 24 into a fraction. It becomes a decimal that never terminates and never repeats. Same thing for cubic root of 4. Any square root, cubic root, fourth root, fifth root, any kind of root that does not terminate or does not come out evenly, like square root of 25 and cubic root of 8, will be irrational. Any non-repeating, non-terminating decimals will be irrational. And we have some special numbers, like pi, that we always approximate 3.14 or 3.142. This is an approximation. Pi is a decimal that never stops and never repeats. Notice that both groups combined make up the real numbers. That means that every number that is on the real number line that we usually write 0, 1, 2, 3, dotted all the way, keeps on going, and every number that is on that real number line is either rational or irrational. So let's talk about what these words mean at the top. Set, finite, and infinite. These two are symbols. This symbol means union, and this symbol means intersection. All right, so let's make two sets. Well, I could call W the set of whole numbers. Okay, so how would I write the set of whole numbers? 0, 1, 2, 3, 4, ... because my whole numbers start at 0 and go infinitely on to the right. Okay, if I were to write my integers and I was going to make that a set, it would be -4 ... going that way, -3, -2, -1, 0, 1, 2, 3, ... Okay, Now, using these two symbols up here, union and intersection, let's talk about what those mean. If I said, what is the union of the set of whole numbers and the set of integers? Now, right now, I'm just going to let W stand for whole numbers and I stand for integers. We won't let that happen very long because there's another number that we use I with, and we just don't use I with integers. But we'll talk about that later. But right now, we're talking about the whole number set and the integer set. When I'm talking about this union of two sets, I am saying what will be the resulting set when I throw both of these sets in the same sack and only count each item one time. We call the items of a set the members of a set. Okay, do these two sets have some members in common? And the answer is yes. Okay, so if we throw both the whole numbers and the integers into an infinite sack, okay, they're both infinite sets, aren't they? Because they both end up going to infinity. The whole numbers goes to positive infinity, and the integers goes to infinity in both directions. Okay, when I put them both in a sack but only count each element one time, my answer is going to be the integers. When I put them both together but only count them one time each, the resulting set will be the set of integers. What will happen when I take the whole numbers and I intersect them with the set of integers? Okay, well, the whole numbers are actually included inside the set of integers. The integers contain more than the whole numbers, but the integers contain every one of the whole numbers. Okay, intersection is what they have in common. So when you say that if I intersected the whole numbers with the integers, my answer would be the whole number set, because that is what they have in common. So there you have the theory for lesson 1. But now we're going to come back and do some problems together and kind of solidify things so that you will remember how to do these problems and how to classify real numbers. All right, so now we're going to classify these numbers. Okay, negative 15, and we want to list every single group that negative 15 will belong in. Well, we know that negative 15 is an integer, okay, because remember the integers are all the negative and positive whole numbers. So this one is an integer. It is also a rational number. Okay, so it can also be a rational number because every integer is a rational number, which means it can be written as a ratio or fraction, and it is also a real number. All right, so when we're categorizing them, we don't want to forget that they're all real numbers. 2/3 is already a fraction, so we know it is a rational number. Do you see the word ratio in the word rational? Okay, so 2/3 is a fraction. And remember that whole numbers and natural numbers and integers have no fractions. Okay, I call them the big hooks that we hang all the other numbers in between. Okay, but 2/3 is rational and real. Okay, now this number, 3 pi, do you recognize pi as one of those numbers that is irrational? Okay, 3.142 is just an approximation. Pi is a decimal that never stops and never repeats. Okay, so this is going to be irrational, and it is irrational, but it is also real, because both the real and the rationals and the irrationals make up the reals. So we're going to put irrational and real. What about the people in your family? The number of people that are in your family. Is that a integer? Well, yes it is. Because remember, the integers include all of the whole numbers and the natural numbers. Okay, so we're going to say the people in your family. Well, this would be a counting number. And the other name for counting is natural. Okay, counting, it's also a whole number. Even though the people you have in your family is not zero. Zero is a whole number, but so are all the counting numbers are whole numbers. So it is a whole number. It is an integer. It is a rational number. And, of course, it is a real number. Trying to squeeze a little abbreviation in each one of those. The area of a round table. What do we know about the area of a circle? A circle is round, and the area of a circle is, do you remember? Pi r squared. Pi radius squared. Since it includes a pi in it, it's going to be irrational, but also real. Okay, so irrational and real. Okay, so there's your board, just in case you couldn't see them while I was writing them. Okay, so now we're going to go with another board. On this board, I have written some sets. Okay, so here the set A is just the numbers 1, 2, 3, 4. These are members of the set and called elements of the set also. Elements, members mean the same thing. And B, set B, is the elements 4, 5, 6, 7. So if I were going to do A union B, now remember union means throw them all in the sack, but only count each item one time. Then, do I have something that would be repeated that I will have to just list once? They both have a 4, don't they? Okay, so when I throw them all in the sack but only count the 4 one time, it's going to be 1, 2, 3, 4, 5, 6, 7. All of those elements will be in the set A union B. Okay, A intersect B, remember intersect is what do they have in common? And A and B, sets A and B only have one item in common. They both have the item 4, number 4. So A intersect B is just the set 4. All right, so look at the board. See if you understand what's there. A union B and A intersect B do not look the same, do they? Okay, they're two different meanings. Right? Here we go on to board C. Okay, in board C, I've defined 2 more sets. And the first one is the even numbers through 10. C is the set of even numbers through 10. Well, let's see if we can write C. C is, we'll write it up here at the top. 2, 4, 6, 8, 10. Oh, I need to be careful because if I didn't say even whole or even anything. Okay, so I'm going to say, well, let's clarify this. Even in natural numbers, so even counting numbers. Let's stick a little counting on there. Okay, odd counting numbers. That will clarify what I'm talking about. Even counting numbers to 10. 2, 4, 6, 8, 10. Okay? And then this one says odd counting numbers to 10. Well, 1, 3, 5, 7, 9 would be my odd counting numbers to 10. Put my little set symbols there. Okay? So these are the listings of set C's items or members. And this is the listing of set D's items or members. Okay, so C union D means I throw C and D both in a sack, and I only count everything one time. So C union D is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, since I represented these with words before, is there a way to represent C union D? Instead of saying the even counting numbers and the odd counting numbers, could I say that C union D is simply the counting numbers up to 10, through 10? Okay, counting numbers through 10 would be a quick way with words to describe set C union D. Okay, set C intersect set D. That's what they have in common. All right, 2, 4, 6, 8, 10, 1, 3, 5, 7, 9. Do they have anything in common? Nothing. So we call this the empty set. The empty set is written in symbols as just two little brackets that are empty, or this little symbol here. Okay, now let me give you a little hint. Sometimes teachers have a hard time discerning what you mean when you put that little symbol. And even if you make your little parenthesis, your little brackets as weird as I do, teachers might have a hard time determining what you mean. So what I tell my students is always this: give me the symbol and then clarify it by putting empty down, or empty set. Okay? Remember, a set is just a grouping of members or numbers. All right? We can have sets of things that are not numbers. Okay? We could have a set of my grandchildren. And my set of my grandchildren, they are going to be 12 in September. Okay, so in September I'll have my 12th grandbaby. So I could start listing the names of my grandchildren. And my oldest grandchild is Michael. And I have a Hannah and a Ruth. And oh, there's a lot of kids to name. But I could name each one of their names. And that would be the set of my grandchildren. And I'll save writing all of those down for another video later. When I need a large group of names, I have some already handy, don't I? Okay, so now we're going to look at one more with sets. And this one is talking about closure of sets. Okay, now closure, a set is closed if the results is inside the original sets. Okay, the set of natural numbers is closed under addition. Now let's look at it. If we have two natural numbers, say 5 and 6, will my answer still be a natural number? 5 plus 6 is 11. Okay, so the set of natural numbers is closed under addition, no matter which two natural numbers I add together. In the whole infinite set of natural numbers, my answer will also be a natural number. Okay, but now let's think about subtraction. Is the set of natural numbers closed under subtraction? The answer is no. What if I take these same two natural numbers, 5 take away 6? Well, 5 take away 6 is -1. And -1 is not a natural number. So the answer, subtraction, is not closed under subtraction. Okay, what about closed under multiplication? Well, let's think about it. if I take two natural numbers, any two natural numbers, 5 times 6, and I multiply them together, I get 30. Is 30 still a natural number? It is. Now, if you think about it, any two natural numbers will multiply together to give you another natural number. Okay, so the natural numbers are closed under multiplication. But what about division? 5 divided by 6. No, that is a fraction, but it doesn't turn into a natural number. So I took two natural numbers and I divided them, and I went outside the set of natural numbers. Therefore, it is not closed. The set of natural numbers is not closed under division. Okay, so the set of natural numbers is closed under addition and multiplication, but is not closed under subtraction or division. All right, so let's look at another set. Okay, the set of whole numbers. Okay, the set of whole numbers, if you took two whole numbers and added them together, would you stay in the whole numbers? Okay, yes you would. Okay, if I took 23 and 33 and I added them together, I will get 56, and that is still a whole number. Okay, if I subtracted those two, then I'd be in a negative number, right? 23 take away 33 is negative. So subtraction is not, the set of whole numbers is not closed under subtraction. Okay, multiplication. What if I multiplied those two together? Yeah, it would still be in the whole numbers. Okay, and even if one of them was 0, I'd still be in the whole numbers, wouldn't I? Okay, so under multiplication, yes, the set of whole numbers is closed under multiplication. What about division? Okay, well, if I took 23 divided by 33, that gives me a fraction. It does not go back to a whole number, does it? So, no, we are not closed. The set of whole numbers is not closed under division. What if we took this right here and we stuck in integers? Integers. Okay, integers would be closed under addition. I could add any two together, and yes, it would be closed under addition. What about subtraction? If I subtracted any two integers, remember what integers are, positive and negative whole numbers. If I subtracted any two integers, would I still get an integer? The answer is yes. So the integers are closed under subtraction. What about multiplication? If I multiply two integers together, do I still have an integer? The answer is yes. The only one that integers don't work for is division. If I divide two integers, I can go outside the set of integers. So this one would stay a no. Okay? But what's cool is if you change this to real numbers, if you change this up here, the set of real numbers is closed. Yes, it is closed under all of these operations. So we would have to change this for a yes, because remember that real numbers not only include all of the big numbers on the number line, okay, but it also includes all of the ones in between. So the whole numbers are closed under addition, subtraction, multiplication, and division. I hope that you have learned a lot about classifying real numbers, and I will see you next time with lesson number 2. May God bless your day.